Testing, 1, 2. Oh, okay, thank you. Kids, go ahead and just sit right over here. Yep. Oh, it's 10:59, so I think we're going to start here in about a minute. We'll make some noise to draw people in today. I don't know if you guys heard some noise over in the junior camp tent this morning. We're going to duplicate that. Oh, thanks. There we go. Wrong way. Need to get some new buttons over here. All right. As soon as I see 11 o'clock, we'll go ahead and get started.
The schedule said 10:45, so we were here early.
That was so you would be here early. Yeah. And so you can get a good seat. Yeah, we're going to call these the hot seats. You'll see that in just a moment. Yeah, it will be. No, flame on, that's right. All right. I think we're going to go ahead and get started, 11 o'clock. Good morning to those faithful that are here. All right. Let's get started with a word of prayer. Father God, I thank you for this amazing world that you've created for us, for all the creatures. And it's just amazing. And I'm glad we get to talk about it here in Washington at camp meeting. And please be with us. Help us to be safe as we run some experiments and show just how amazing you've designed this world. Be with us now, we ask in Jesus' name. Amen. All right, today, the topic for part 2 is called Don't Touch That Dial. And there's a lot of things about fine-tuning that we're going to talk about in the Earth's atmosphere. So as a quick review from yesterday, I'm going to get Carter to come up. And he was just messing around with this water bottle. Come up here. You don't need the headset yet. The ear blockers. All right, Carter. So Carter, what did you do here? Let's see. He put a hole in the top. And he was playing a little trick on us, thinking they had the cap on, and he was sucking the water out of it. So what did I tell you to do?
Tip it upside down.
So I told him to tip it upside down. And so now he's making a mess. You guys can see the water is dripping out. I don't know if you can eventually. Okay, we got a little water spot here. It's okay, it'll dry up. Okay, there you go. Yep, just hold it steady right there. Now, what is holding, now why is the water not coming out as fast? Yeah, we created a little vacuum in here, and the air pressure is enough to hold it inside. And then it will stop. And actually, the heartbeat is enough to kind of change the pressure inside of there. And I thought that was really cool. Good job, Carter. Yeah, you did it. So the air pressure is holding it in. You can do a lot of fun things with air pressure. Good job. You can take back to your seat here because we're going to put some other things on here this morning. All right. See if I can get this going here. So we're going to talk about the other ingredients in the air today. So the two main ingredients are nitrogen and oxygen. We're going to talk about that. And also carbon dioxide. I don't have too many experiments with argon, but I've got quite a few with these 3 ingredients. We're going to apply our chemical design thinking to these 3 elements, to these 3 compounds actually that are in the air. And so I've got a bunch of experiments. I've hidden them underneath here this morning. So we'll be pulling them out. I've got quite a few things. I normally do this as 3 one-hour long talks. So we're just going to do it in 1 hour and 15 minutes today somehow. So with the Lord's blessing, we'll do this. So just as a reminder, some evidence, I think, of chemical design. If there's some bad things that happen if you have too much, we want to note that. What happens if you have too little? What's up with that? Is it dangerous? And how do we know we're in a finely tuned position that we have the right amount? So we're going to go ahead and get started with oxygen. So oxygen is at 21% in our air. And why is it at 21%? Is there something fine-tuned about that? Or, could it be at another level? And it can, and it can fluctuate a little bit. But how much? Because people have these ideas that maybe the Earth had maybe 30% oxygen at one time. And, what are some benefits that it could have? Maybe creatures were bigger because of that, and plants were bigger because there was more oxygen. I'm going to probably call that in the question today, and you will see why in some of our experiments that we're going to do. So what is oxygen? Well, it really isn't just an oxygen atom that's by itself floating around. It's actually two oxygen atoms double bonded together. And so I have my little picture of that here. And so we call it O2, or dioxygen. And that's important, actually, too, that it has some chemical structure to it and its properties. We know that it's important for life. We know it's important for fires. So we're going to go into more detail about that today. It actually is a little bit like oil in the sense that it doesn't want to mix with water, and we'll see why that's important later on. It is a gas, so it's up in the air. It's floating around. That's important to note as well. And it is actually a very, very reactive molecule. Once again, we'll demonstrate what that means here today so you can get the full power of that. And one of the first evidence of design that I want to talk about to get everybody's attention here is what happens when you have these really light gases. So people often guess, if I say what's in the atmosphere, I'll hear helium, I'll hear hydrogen. Well, the Earth's gravity is such that when you get a balloon here, I've got one of helium, and these are wonderful little balloons, right? And what would happen if I were to let go? Are you sure? Oh, man, there it goes. Okay. Now, when will it stop? Now, it stops when there's a ceiling here. What if you let a balloon go with helium on the outside of a building? Where does it stop? It just keeps going. So helium in itself actually will escape Earth in its gravity and go into outer space, and it's gone. That's why we actually don't have that much helium in our atmosphere, or if there is, it's very, very, very little. Now, hydrogen gas is the exact same thing. It will go and just leave our planet, and that's a very, very important thing, that if our Earth was any bigger, it would actually, the gravity would hold on to helium, it would hold on to hydrogen. That's what Jupiter does. And these large planets, they hold on to these gases because of the gravity. So if they talk about these really large Earths, I'm a little curious on what is in the air at that point, because it could hold on to these really light, low-dense gases. So it's a great thing that the hydrogen, it would be nice if the helium would stay, because we can make more balloons that way. There's often helium shortages. We actually don't know how to make helium. It makes you talk funny. We'll do that one tomorrow. And we've got some other things that we can do with that tomorrow. So, yeah, we could have more balloons. It would be cheaper. We have to actually capture helium as it's coming out of the ground from radioactive processes. We can't actually make it any other way. We just capture it. So we're glad that these light gases actually leave the planet. So one could say, boy, it's sort of ironic, or it just so happens, you're going to hear me say that a lot today, it just so happens, it's a coincidence that the Earth is the right size so that these light gases could go away. We're going to find out what happens if we did have a lot of hydrogen in our atmosphere. So I thought, I captured a few, so I have some tanks of hydrogen and oxygen. So I've got some helpers back here. My team is back again. And I've got all these special balloons in here, and unfortunately I put the one I wanted, I think, near the bottom. Okay, oh, there's that. I got an extra weight that I may need today, so we'll get that out. And kids, are you ready? Carter, why don't you go ahead and come on out and get the stick ready. And we are going to light some balloons here with different gases in them. We did this for the juniors this morning. I don't want to lose any. We're going to do oxygen here. This one's O2. This is what we really like. We know this is an important fuel for fires. Maybe we should have Christiana do this one. Well, you can help get it lit. Christiana, are you ready? You ready? Okay. So I'm going to get some of my stuff out of here. Get my glasses on, just okay. I think you guys should be safe. The only thing we had happen was our little clips went flying this morning. Not very fast either. Okay, why don't you go and hold on to this one? Hold on the end of the stick. You saw how to do that. Okay, Carter. Okay, back up. Carter's going to light it. And be thinking about what happens when you light a balloon with oxygen. You may want to plug your ears. Christiana's going to sneak right in there. Okay, that was not very exciting, Christiana. Couldn't you do any better? It's not you, right? It's the oxygen in there. So oxygen in itself doesn't burn. We need a fuel to burn. So we are going to use one now that has some fuel in it. And we're going to use hydrogen as our fuel today, that really light gas. And so I have a H2. That's actually what hydrogen gas is that gets made. And we're going to repeat that experiment. I'm going to pull it back here a little bit. Probably burn the blanket a little bit. This one will produce a little bit of a fire. And Carter, are you going to do this one? Okay. And here we go. Carter, go and sneak that candle. This one will make a little bit of noise. It's not too bad, and there will be some fire. And he's going to sneak it right up. There you go. Woo! There was some noise in that. Wow! Oh, yeah. Thank you, hydrogen. All right. Are you going to do the next one? Okay, I'll probably do the next one. Okay, but I'll need your help, though. All right. Okay, good. We kept our thing. Oh, okay. Okay, go ahead. You can just go. All right, this one. Oh my! I've mixed oxygen. Ooh, keep that flame away. Okay. This one I've mixed oxygen, which we need to burn, help burn. Okay, Carter, why don't you go ahead and light that one? And this one will be loud. And my kids took my headsets, that's all right. And we might want to turn the microphone off. Whoa, okay, we turned the mic. I do that in my classroom all the time, so I think we might have lost something, but all right, everybody okay? Let's set that off to the side. Wow, that was awesome. I do that in my classroom all the time, and the kids, I love that. All right, go ahead and sit down. Thank you for bringing that back. All right, you okay, you guys? All right, go ahead and have a seat there. Woo, man. Hydrogen and oxygen. Was that a nice mix? Yeah, I mean, it was if you like explosions, right? Whew. So this could potentially happen if our gravity was large enough, it would hold on to hydrogen, and these kind of things could be a real risk. Now, you have to have the right mixture in there, and I had a nice 2-to-1 mixture, and those just made water. That's a fun way to make water. Okay, sorry, hun, I burned the blanket a little bit. All for science. Okay. All right, so it's a good thing that we don't have these really light gases in there as well. Now I have a little joke on the screen there, if you guys could get that. It's also good that we don't have a lot of helium in there, so laughing gas. Hee hee hee. All right, I keep forgetting to put some of those fun ones in there. I just saw some balloon fragments fall there. All right. Let's get into more about oxygen, and you guys are very familiar with what happens to the oxygen levels as you go up on a mountain. You guys got an experiment you can run anytime you want, just down the road here with Mount Rainier. Now, Michigan, this is an unfamiliar thing. Our mountains are, a couple hundred feet high. You spend more time going up the hill than you do going down the hill, and maybe that's true with all mountains, but so. OSHA and others and scientists have figured out, well, if you get down to about 17% oxygen, it's really hard to breathe. And as you get down to lower levels below that, then obviously it becomes very hard to breathe and to operate. So for large creatures like us and bigger ones, about 17% is where you start to really lose a lot of your cognitive abilities. You just aren't able to function properly, and it gets worse the lower you go. So 17% is kind of a lower limit for large creatures and organisms that use oxygen, which is basically all of them. So I like to think of that as a lower limit. Anything below that is not good, and OSHA would testify. Those are some of the limits that they've set. Now, what about some of the higher end limits? What would be a higher amount of oxygen? Okay, OSHA, what did they say? All right, so anything lower than that is bad. So what about too much? Well, some of you may be familiar with these things called hyperbaric chambers, and that's where they actually increase the oxygen concentrations in there. And it is amazing. You can have some pretty amazing healing, acceleration in your healing if you have some injuries, surgery, or something. And so this is a picture from the Mayo Clinic, and they are helping to advance some of the treatments using hypobaric oxygen, just high oxygen concentrations. So you might be saying, oh, wait a second, God, why didn't you put more oxygen in our planets? Because if that's better for healing, that you're a bad designer, because you didn't put nearly as much oxygen to keep us from healing as quickly as we could. Well, it turns out high oxygen concentrations are only good for a short amount of time. And so some of their warnings, as you may read there, include, and some of them are just from high pressure. You could blow out your eardrums or your lungs. That sounds terrible, and it is. But if you read on, one of the last warnings is that they say if you're exposed to high levels of oxygen for too long, there's something called oxygen toxicity that will set in. And oxygen's so reactive, it just starts to break down your tissues, and some of the early symptoms are dizziness and nauseousness, and it can get worse than that. Now, scuba divers are all aware of this, and so, but anyway, I guess before I go on to the scuba divers, there's an upper limit, and I wonder what that is that we should be breathing. Now, you can breathe pure oxygen for a short amount of time, a couple hours maybe, but you can't breathe it day in and day out. It will scar your lungs, and it's very damaging. So divers know about this as they make mixtures of gases as they dive down low. They know they can't put too much oxygen as you get into higher pressures going down deep in the ocean. That will concentrate those gases in your bloodstream. And so they know that something called oxygen toxicity is a real thing, and if you have too much oxygen in your mixture as you're going down, it'll concentrate, and this toxicity can lead to unconsciousness and eventually drowning if you're not paying attention. So you can't just have tons of oxygen and go, man, give me more oxygen. If a little is good, a lot is better. No way. I don't see that in science anywhere, where if a little good is a lot better. I don't know where that came from. Maybe from eating chocolate, I think. A little is good and a lot's better, right? Dessert. No, we know that. I mean, we should get rid of that. If a little is good, a lot is better. I don't know where that came from. That's just wrong on all levels. And I've got the hips and my stomach to prove that too much is bad. So of everything. Okay, except for love, right? If a little love is good and a lot of love is better. All right, so there's definitely an upper limit. Now, what is it? I don't really have a good read on it. I'm just going to put a number out there, about 40 or 50% in terms of what we should be exposed to on a regular basis if you're designing a planet. So at the lower limit, we just don't have enough oxygen to function properly. At an upper limit, maybe around 40%, you get some toxicity to set in, especially the longer you go. But there's something else we need to consider when it comes to dealing with the upper limit. It's not just about what do creatures need to breathe. There's another issue that comes in, and it has to do with how reactive oxygen is. And we saw some of that reactivity with hydrogen here already. Now, things like iron, pure metals, when you set them out into the air, boy, they react with oxygen and they rust. Okay, so that's because oxygen's reactive. It will do that with basically any pure metal. There's some pure metals like gold and silver that resist that. Others will rust in various ways. Iron has done it spectacularly. I think most of us can remember seeing a lot of these rust buckets. Is that a problem up here in Washington? Michigan, man, growing up, rust was everywhere, and we're still fighting rusty cars. Now, you know this from a biological level as well. Oxygen, when you cut open a fruit, it will bruise, and typically, I hear that they're designing genetically new fruit that doesn't bruise. Okay, sounds interesting. And hopefully there's no other issues. Anyway, that's another topic for another time. But most fruit, when you puncture the skin, the oxygen starts to react with all of the chemicals inside, and they turn colors. That's a chemical reaction. That's reactivity. So we know that oxygen's a very, very reactive molecule. We don't want too much of it around. We want enough to power ourselves and to power other important chemical reactions in our bodies for energy. And I was reading this book because I wanted to learn more about oxygen, and there was a book called Oxygen, the Molecule That Made This World, and it's not necessarily, it wasn't written by someone that believed that God created this world. They wanted to show how oxygen prompted the evolution of creatures, and it's interesting. Those stories always talk about how life has to be involved in the production of oxygen. But in there, I found it interesting that there is really not a good way to power big creatures other than using oxygen. And he made the statement in there that it's hard to come up with a way to create biological energy without oxygen. If you did, it's about 4 times less energy there. So we really do need to have oxygen, and a lot of it, we appreciate its reactivity, but it has to come at a certain level. So in order to get energy from oxygen, our biology is set up to deal with that, and only to a certain level. So the other reason we need to think about what the oxygen levels are, a designer has to think about fires. So I'm going to go to my next little demonstration here. And Carter, why don't you come on up? And yeah, we'll have Christiana come up for the next ones here in a little bit. Carter, you're going to light this candle here. And I've placed the candle in some water, so we can get these guys to zoom in. Appreciate all the AV help. And what would happen if I were to cover up that flame? Go out. And why does it go out? Yeah, it uses up the oxygen. Okay. Now, I don't know. We're going to do it one more time here. Hopefully we don't get the candle too wet. Carter, you may have to let it burn there for a little bit. So you guys were focusing on the flame. And what we want you to do this time, if we can, I might have to knock out some of that water there. Oh, good, I got a little. No, he's going to try to get that lit. It's kind of wet. Here, let me knock off some of the water. All right. Now you try to light it again. So this time I want you to focus on the water level, and we'll see if we can pick it up. Yep. Oh, good. It's going to go. So this is a fun experiment to do at home. Put a candle in some water. You have to find a way usually to weight it so it stays down. And then cover it up with something I like to use. I have a graduated cylinder here. Now as I put it over and the candle goes out, the water level, I don't know if you guys can see it, comes up inside here. And you can kind of measure the percent of the air that gets used up doing this experiment, and you get kind of close to 20% of the volume gets used up from that candle. And so the candle goes out, and we can show that the oxygen is getting used up. So we obviously know that oxygen is very important for fires. Can you go ahead and sit that down to the side there? Okay. And I wonder, well, what is it about oxygen and fires that we should learn about? So for our first video here this morning, I train my chemistry students to use a Bunsen burner. This is my little video I made for them. And they have the little Bunsen burner there is hooked up to methane, natural gas, and we're going to roll the first video to show what you should think about when you are lighting a Bunsen burner. Okay, this is how we're going to set up the Bunsen burner in our lab. You'll notice here's a gas valve to turn it on or off. And this is our Bunsen burner. It's a little bit different from some other videos you may have seen. There is no additional valve. All we can do is open and close the valve stem to let in oxygen through here. Okay? The gas comes through the hose and it mixes with oxygen in this area, and that will cause our flame. It's best to get it started with it all the way closed. You can go ahead and open it all the way, or you can control the amount of gas by the valve right here. Other Bunsen burners have it on here. We do not. Come in from the side, and using your striker, create a spark. And you can see a nice big flame. It's a bit too big. And you come back to the valve, and we can start to shut it, and that'll reduce the amount of gas that's there. All right, this is a bright flame, but it's not actually burning the gas very well. This is called incomplete combustion. There's not enough oxygen. And so there's a lot of particles still unburnt that are causing a lot of the color, the yellow color. To make it hotter, we can open the barrel by turning it counterclockwise, and it'll allow more oxygen into the flame. And you can see now a blue flame starts to show up. This is getting hotter now. Blue is hotter. And the more oxygen that I let in, the hotter it will get. And eventually you should start to see when it gets very hot, there is, it almost looks like there's two flames, an inner cone and a larger flame. The inner cone, the tip of it, is the hottest part of the flame. And so that's our basic operation of our Bunsen burner. Then you can move your crucible and whatever you needed to on top. It's very hot, of course, up here. Now to turn it off, or in case of emergency something happens, you can turn it off right here. And that's it. You're done. So be careful. It could be hot. When you're done, give it a few moments to cool down, and it should be just fine. That is the operation of our Bunsen burner here in General Chemistry Lab. Don't forget the location of the gas valve near the door that controls all the gas in the lab. If it's on, you'll see a red light. If it's off, you will not see the light. In fact, let me give you another little, oh, there we go, another view of that. So this is well studied and well known by welders and chemists alike, that bright yellow flame is actually kind of cold. Cold to you would still melt your skin, 300 degrees Celsius. But as you open that Bunsen burner up, you allow more oxygen in the air to blend in with the natural gas. You can get the temperature up to 800 degrees Celsius, maybe even to 1,000 degrees. If you're able to mix it with pure oxygen, you can get natural gas to burn it somewhere around 2,000 degrees Celsius. And of course, welders know this because if they take acetylene with pure oxygen, they can blend it and get up to maybe 3,000 degrees Celsius. So it can get really hot by controlling the amount of oxygen in the flame. You want it hotter? You want more things to burn? You put oxygen in there at higher levels. Now this reminds me of the story in Daniel. I'm going to get my little device here. And I love that story in Daniel where it talks about Shadrach, Meshach, and Abednego, and they would not bow down to the king's idol. And there they were faced with the pressure of burning in a furnace. And so the king was so mad when he gave them even a second chance to bow down, and they refused. I love that story. And what's interesting is the king knows that we got to make the fire hotter. So he says, go make it hotter 7 times. And so even some commentaries will say, well, they put more wood on the fire. I don't think they did that. and they knew at that time how to make them hotter. And they probably had some big bellows that were able to pump in more air, which had more oxygen, and get that oxygen ratio up there. And maybe they had big bellows and they did it 7 times or something to get more oxygen in there. And so these are nice. You can still get these at the hardware store somewhere. I think I got it at Home Depot or someplace, $9, and we have fun with our fires trying to do that. So we learned that you need oxygen to make flames and fire hotter. So that oxygen level that we need to think about now has to deal with fires and making them hotter. As I've looked around at different firefighting websites, they talk about they don't want any more oxygen around. If you're a firefighter, you know, if there's oxygen tanks or you don't want any higher oxygen is bad. But OSHA actually set some upper limits on that. But there's some interesting quotes from some of these websites here, if I can get to and read it. In an oxygen-rich atmosphere, such as in areas where medical oxygen is in use, or high-pressure diving or medical chambers, combustion is greatly accelerated. More oxygen, fire burns faster. Materials that resist ignition or burn slowly in air can burn vigorously when additional oxygen is present. So combustion starts at around 14 to 16%, and it just gets better the more and more oxygen you have there, the higher concentrations. OSHA wants to set the upper limit basically around 24%, 23.5%, 24% in a room. So, man, if you talk to OSHA, no more oxygen, please. There's enough there. Firefighters, no more oxygen. It's hard enough to fight a fire where we are right now with the oxygen levels. So where should we set the upper limit? Well, OSHA does pretty good. 23, 24% is probably a good number. So if you think about where we are in terms of our oxygen levels right now, we're kind of in a good level to have good fires and to have large creatures coexist at the same time. So I find that 21% is actually at a very nice in-between level before fires get out of control. And if with higher oxygen concentrations, things that burn or that don't burn could start burning. So having an oxygen concentration around 30% with our given pressure, that's probably not a very likely thing to have occurred. Otherwise, we would lose a lot of vegetation with that. So one more thing about oxygen. Man, I've got a lot of things on oxygen, but we're going to talk about one more thing, and that has to do with oxygen and how it's needed for how oxygen in water is needed for sea creatures, because fish and other gill outfitted creatures, they need oxygen in the water. And so how does that relate to the oxygen that's on top? Where do they get the oxygen in the water? Well, it turns out that the oxygen that is in water is the exact same oxygen that you and I breathe. Some people say, well, no, it's H2O, right? That's the oxygen that fish breathe, the O part of H2O, and that's incorrect. And I have a little experiment here to demonstrate that. Maybe Christiana, you can come up here and do this one. So in this container, I have a substance called methylene blue. All you need to do is just pick it up and shake it around, okay? All right, can you do that? Okay, good job, perfect. Okay, keep shaking it some more. All right, keep shaking it, hold it up. There you go. Oh, you're doing great. Perfect. Yeah, look at that nice blue color that's there. Okay, let's go ahead and set it down. Let's see if those guys can zoom on that. Very nice. So what's happening in this experiment is the oxygen that's in this part of the flask is being mixed inside with the water. It's being pushed in there. And when that oxygen is there, there's a molecule that turns blue. And I've seen that the color is going away. I don't know if you guys can see it, but for me, it is. Can you guys see that? It's kind of gone away, and on camera, it looks like it's still there a little bit. Maybe it's holding in front of your coat. No? Let's see if we can make. And if we shake it some more, we can get that dark color to come back again. And so that mixes with more oxygen. Thank you for your help. You can go and sit down. Okay? And we'll keep our eye on that. And so the color goes away when the oxygen is used up. I have a chemical reaction that's using the oxygen up. So that's pretty exciting to know that it's oxygen that's getting inside of water that is the exact same water or the exact same oxygen that we breathe. So there's a law called Henry's Law that helps us to understand how the pressure of a gas on top of a liquid tells us how much gas gets inside the liquid. So something I teach in my general chemistry class. It's the same technology they use to put carbon dioxide into your sodas. They have high pressure carbon dioxide, and that pushes more carbon dioxide into the liquid. So the more, if we had more oxygen on top of water, it would push more oxygen inside. This process of dissolving oxygen into the water is actually really inefficient. So if you're to convert 21% into this other unit called parts per million, there's 210,000 parts per million of oxygen. There's a lot, but only about 9 parts per million oxygen end up in the water. Very little oxygen is dissolved in there. If we had more oxygen, we could get more into the water. And if there was less, there would be less there. Now, 9 parts per million is plenty enough for sea creatures and fish with gills to work and to operate properly. So the gill system with its membranes very thin allow oxygen to pass through, and they're able to get enough oxygen there. Whole nother thing about what happens to fish when they jump out of the water. But basically, the point is they're breathing the exact same oxygen we are, and it's the very little that gets pressed inside of the water as oxygen is sitting on top of the water, pushing itself in there. Okay? Now, each gas in our atmosphere has a very high level, but only a little bit of those gases end up into the water. And it's like each one of our gases, nitrogen, oxygen, and carbon dioxide, all have their own dial that's been set to allow the right amount of gases to be pushed into the water so that fish and plants and things have all the right oxygen that's in there. Now, it doesn't take too much oxygen before it becomes toxic for the fish, and they can get things called gas bubble disease and like the bends for us. And too little, of course, they die off. And this is such a finely tuned balance of oxygen in here, and it's totally controlled and dictated by the amount of oxygen on top. In fact, one of the clear evidence, I think, of this balance being there is all the fish kills that happen. Just type in fish kill in the internet, and you're going to find tons and tons of pictures about fish dying because of the lack of oxygen. And boy, I can just show you pictures of pictures of just a whole schools of fish dying off all at once because of low oxygen levels. And I have a video here of some fish kills that happen. This one in Florida, you can find all sorts of videos and things. So if we can roll that second video on the fish kills, thank you very much.
Florida is known as the fishing capital of the world, but right now there's a lot less fishing and a lot more concern about what's happening to their valuable and vulnerable ecosystem. If you walk up and down Indian River Lagoon, you will see this. Thousands of dead fish belly up in the water. There are several different factors going into play here. One is the state received about triple their average rainfall for the month of January. All of that rainwater and runoff has gone straight into the rivers and the lagoon. Not to mention, because of El Nino, temperatures were warmer than normal, allowing for a toxic algae bloom and brown tide to take over. The algae bloom depletes the oxygen from the water, in turn killing the fish, and has also killed more than half the lagoon's seagrass. The Florida Fish and Wildlife Research Institute says the fish kills happen all the time, all over the state, but this one is massive.
It's basically, these fish kills happen. And it's funny when you talk to the biologists and you see them reporting on this thing, this just happens. And it does, it happens all the time. That's because there is a process called eutrophication. I think I have a slide on that. And eutrophication, if I can simply describe it, if a lot of fertilizers end up into the water, they help the plant life and a lot of bacteria to grow really fast, and they start to consume too much energy and resources, and then they run out, and then they die. When they die, there's a lot of other bacteria that come in, and they consume oxygen as they basically start to use up all these dead organisms, and they're living off of that. And that uses up the oxygen and sucks it right out. If there was plenty of oxygen, this wouldn't be an issue. But oxygen is finely tuned, and that becomes an issue, and lots of fish die off. So eutrophication, nice big word there. One of the last things I want to say in the finely tuned balance of oxygen, and I have lots of experiments to show these things, so I'm cutting out quite a bit of this. This picture that I'm showing in my PowerPoint slides is a slice of the Earth. On one end of the graph, it shows Antarctica, and the other end is Greenland, where it's really cold water. So you may have experienced this, but cold water wants to sink. It's actually more dense. It has a greater density, and it will sink down. This is amazing. Henry's Law and cold water, we actually learned that there's more oxygen will dissolve into cold water. And this is pretty neat. So actually, we shouldn't feel bad for the fish in Lake Michigan when it gets cold. They're actually able to breathe more oxygen at that point. There's more oxygen being dissolved at that point. So they like it when it's cold because there's more to breathe. But in the design of our planet, there's something very interesting called the Great Conveyor Belt. And the poles, as the water gets cold, it's able to hold on to more oxygen, and that cold water with more oxygen is able to sink down, and as it comes towards the bottom and actually will heat up, there's a lot of vents that are expelling a lot of heat and materials from the bottom, and it warms up the water, and that actually then releases some oxygen, and then the water actually comes back up because it's warmer and less dense and floats up near the equator. And you get this conveyor belt that's going, that's mixing the oceans all the time. That's amazing, and it just has to do with the density differences between hot and cold water. But it's delivering oxygen down to the lower levels of the ocean floor. It's amazing. And if it was the other way around, you couldn't have creatures that utilize oxygen at anywhere in the ocean other than near the top. So it almost turns out near the top there's less oxygen, especially near the equator. And so the creatures know this, and they swim away. So there can often be dead zones of low oxygen level if the water's too hot, and mainly through that. So not only is the oxygen being equally and well mixed and because of the density of hot and cold water and because of the Henry's law effect of dissolving oxygen, that oxygen also serves as a protective effect on a lot of the things that are coming out of the bottom. A lot of hydrogen sulfide and other chemicals are coming out through these black smokers, and the oxygen is so reactive it's deactivating a lot of the bad chemicals that are coming out from the middle of the earth. So it neutralizes them. So we're thankful for the reactivity of oxygen. And all of this just happened. It's amazing. So I'm going to recap oxygen, and we're going to move on to carbon dioxide. So let's think about all of this real quick. Oxygen, so Earth's gravity, we're just the right size to hold on to oxygen, but let hydrogen go. That's pretty cool. All right? Now we have oxygen levels that are pretty much good for us, and for many creatures, we can go all sorts of altitudes. Now there's limits, but we can go almost anywhere we want on land without having to worry about it. It's safe enough for fires and for cooking, so we can process things with fire. We have enough oxygen on top that pushes oxygen inside for water, into the water, so that we can have living creatures in the water. We know cold water holds more oxygen. Cold water sinks, and that allows it to go to the bottom. And we can get lots of power from oxygen when we breathe. The respiration is a very powerful activity. And one thing I didn't mention, but that oxygen in the air, if it helps fires, it helps the debris that's coming in through the atmosphere to burn up as well. There's other things about oxygen that I will talk more about tomorrow on how it creates ozone. We're going to talk about ozone tomorrow and how it blocks the sun's radiation. That's really helpful. And something that I also didn't mention is that oxygen is not a greenhouse gas. We'll talk about greenhouse gases in just a few moments. So, and then we'll talk about plants and how all of that is just recycled naturally for us. So I see that oxygen's at a very finely tuned level. It can be a little higher, a little lower, but there's implications there. So I see some chemical design when it comes to the level of oxygen in our atmosphere. All right, let's talk about the carbon dioxide. I'm going to save nitrogen for last. And people like to overlook that molecule anyway. So I like to call carbon dioxide our heavenly blanket. Heavens meaning the atmosphere, and blanket, of course, keeping us warm. So why is it at 0.04%? Actually, it was a little lower. It's been kind of going up. We're getting worried that our blanket is getting a little too thick. So let's talk about that for a moment. When we breathe in, we're taught that in elementary school that when you breathe in, you're breathing in oxygen, and when you breathe out carbon dioxide. So it's interesting. If this is what you're breathing in, 78% nitrogen, 21% oxygen, 1% argon, and now 0.04% carbon dioxide, what are you breathing out? What do you guys think? It's just all carbon dioxide. That's what I was taught in school, right? Yeah. No. That's why we have to do these things. Nothing touches the nitrogen. That stays at 78%. What happens is a few percentage points of the oxygen get converted, about 4 or 5%, and that combines with some of the food, and it creates carbon dioxide. So yes, the carbon dioxide levels do increase, but it's not all carbon dioxide. And that's actually very important, because if it was all carbon dioxide that came out of our breath, we probably could not jog in place. We would faint because of the high carbon dioxide levels. If we were in a closed room, it wouldn't take long for a bunch of humans to turn the oxygen over into carbon dioxide. So it's a small turnover that takes place. And I didn't realize that, because I remember I had my PhD in chemistry, and I got a hold of a carbon dioxide sensor. I thought, yeah, I'm going to measure this. And on Friday afternoons where I was working for this company, we'd have a meeting that was in a small room with no windows, tightly enclosed at Lintech. I don't know if my wife remembers this. And it's a small room. I brought in a carbon dioxide detector, and I thought, man, I'm going to watch these carbon dioxide levels go up, and that is going to explain why I always fall asleep in these meetings. I finally have proof. And I'm sitting there with this carbon dioxide detector, and the levels hardly go up during the meeting. I'm like, but I was told that we breathe out nothing but carbon dioxide. And then I thought about, we're not actually turning over a whole lot of carbon dioxide. So there, through the meeting, I still fell asleep, and the carbon dioxide levels did not go up very well. So there must be another reason why I was falling asleep. Okay. All right. So you can't blame it on CO2. All right, so where does CO2 come from? Well, it's in there in our air. It comes from us and from living creatures. Actually, plants at night will produce carbon dioxide. They do a form of respiration at night when there's no sun. And a lot of activities of burning and volcanic activity, they're producing a lot of carbon dioxide. So just as a review, 78% nitrogen, 21% oxygen, and this last percent contains, well, what's in this last bottle? In this last percent here, we know if we divide that into 100 bottles, I just want you to get just a real good view of how little carbon dioxide there is in our air. If you take that last bottle, divide it into 100 bottles, 93 of those bottles are going to be argon. And so 4 of those will be carbon dioxide, and then all the other gases fit into the last couple bottles. Do I have them? Yep. All right, so those last few bottles are just all the other things, and pollution and all the other things that end up in the air, ozone. And so there's very little carbon dioxide, but that molecule is, well, we're going to find out, has to deal with our global warming. In fact, that's the molecule that's in the news a lot when they talk about global warming and climate change. And the levels have been increasing since it's been measured in the 1960s. And this is one of the jobs I would like to get. It's out in Hawaii, and they're measuring the carbon dioxide levels away from most civilization. So, Susie, we should try to get a job there. Does that sound good? Yeah, okay. She's nodding her head. Yes, I think. So that'd be great, measuring carbon dioxide levels out in remote locations. And there is seasonal fluctuations, but it's been going up. And this is the concern that everybody has. And I'm not going to address that too much, other than the world is making the case of fine-tuning for carbon dioxide. Too much, and they talk about climate change and all the catastrophes that can happen. They're making my argument for me. So just go read all the news articles. What would happen if we had too much carbon dioxide? And we're not talking about going up to 1%. We're talking about 0.04 to 0.045%, just small increments, disaster, disaster, disaster. And there's probably truth in some of that. And so I wonder what the Lord has in store to take care of a lot of these things. And it's a very complicated topic, and so we're not going to get to address all of it here. I want to address some big issues that people don't talk about. What is carbon dioxide? It is a single carbon atom double bonded to 2 oxygen atoms. It doesn't mix with water too well, but it does a little better job than oxygen and nitrogen. It's colorless, it's odorless, it's a gas, and it's very heavy. We're going to do a fun experiment with it in just a second. But I need to train you on one thing. Carbon dioxide, when it mixes with water, it will dissolve in there, but it does a chemical reaction. It makes carbonic acid, H2CO3. So I need you guys to remember this. When carbon dioxide and water mix, it makes what? Carbonic acid. So let's do it one more time. So if carbon dioxide and water mix together, it will naturally make carbonic acid. Okay, that's important. That is the natural way that water and carbon dioxide react together. If you don't do anything special to them, carbonic acid. That'll lower the pH, and it's going to do some fun things, which I'm going to show you in a little bit. All right. Now, carbon dioxide, heavy gas, and not good for you. It's very toxic in the sense, as you will find out here. There is a lake called Lake Nyos that's at the top of a volcanic mountain in Africa. And this lake sets inside of a crater, and so what's interesting about that is that wind and air as it goes by doesn't really disturb the lake. And over many years or decades, the volcanic gases were bubbling up underneath this really, really deep lake. That's important because if it's deep, there's a lot of water sitting on top. And it actually trapped a bunch of carbon dioxide and other gases, but mainly carbon dioxide, at the bottom of this lake that's up high in a mountain inside of a crater. At one point, there's a storm or something came along, and it disturbed the lake enough, and essentially the lake burped, and all the carbon dioxide came out, and it went down the side of the mountain, and unfortunately, it went into a town, and it was at night. And those that were laying down at night there died. And 1,700 people died, basically smothered, because carbon dioxide is so heavy it pushes oxygen out of the way. Those that were standing up, walking around, lived through that experience. And you just can't see that happening because it's a colorless, it's odorless. You would not know it's happening other than that people are just dying all around you. So that's very scary. But it illustrates one of the properties, a couple of the properties of carbon dioxide. It's not good, and it's heavy. And so we've kind of done the experiment already with those really light gases of hydrogen and helium. Those guys, well, they'll leave, they're light. And steam also will go up high. But carbon dioxide, argon, and ozone are really heavy gases they want to sink down. I think I have it on. Yep. Okay. Let's go back to here. I'm going to do an experiment. I'm going to create a bunch of, Carter, I'm going to need your help now. Carter's going to light some candles in here. And I'm going to create carbon dioxide by the age-old tested method here of using vinegar and baking soda. And I've already set some of that up here, and once Carter gets these candles lit, they're at different heights. We're just going to make a bunch of carbon dioxide so you can see what happens here. So this is our replication of the Lake Nyos experiment here. And the candles then are, of course, are a lot like us. Now, I used to do this with a lid on here, and I said, wait a second, if I trust carbon dioxide, it's heavy, it should just stay there at the bottom and start to fill up. I don't want to make it... So we're going to keep an eye and see what candles get extinguished first. Do you guys seeing that? Yeah, there goes one, the lowest one. So this is just vinegar and baking soda. And it's making that very heavy carbon dioxide. And it's filling up the bottom, and as you can see, the lowest candle went out, then the second one, and we'll see if that top guy can go out. I'm going to make it, oh man, there goes a lot of it. All right, that'll put it out for sure. We'll find out. Hey Carter, maybe you could try to relight some of those smaller ones there while that other one, and see. Oh, okay, come on. You can do better than this. Okay, why is that going out?
It's a carbon dioxide.
That's right, the carbon dioxide is actually extinguishing the flame. So we'll let that go there. Thank you, sir. You can go back and sit down. We'll see if that flame will go out. I'll put a little bit more in here. It can build up quite a bit of carbon dioxide in there, and we'll just kind of let that go. And I like making messes, and as long as we clean them up. It's one of my favorite phrases. It looks like it's, oh, there it goes. Oh, wow, so we know that's up to there now. Whoa, that's cool. And there it goes out. I just can't light it. So that's a great way to visualize the heaviness of carbon dioxide. Now imagine if we had more carbon dioxide in our world, or a lot of argon. Argon works in the same manner. Imagine, if you would, valleys, basements. If carbon dioxide was so heavy, it could start to fill up and go down and displace oxygen. And things like valleys would fill up, and there would be warnings. Do you guys ever have a carbon dioxide warning? Don't go in this valley? No, it's not even anything we have to worry about. Why? Because there's so little carbon dioxide in the air. So it's nothing we have to worry about. So, but if we had a lot more, what are those levels? Well, they certainly, if it was 100%, that's a problem. We actually use this in our lab to displace oxygen out of a container. We fill it with these heavy gases. So it's something we do all the time. All right, so if it's any higher, we would have all of these warnings. And we're going to watch another video of the carbon dioxide. NASA's visualized the levels throughout 1 year. So we're going to watch a video on these levels of carbon dioxide throughout the year. So go ahead and roll the video.
Australia, contributing to high concentrations in the atmosphere. Notice how these emissions are also transported by winds to other parts of the world. As summer transitions to fall and plant photosynthesis decreases, carbon dioxide begins to accumulate in the atmosphere. Although this change is expected, we're seeing higher concentrations of carbon dioxide accumulate in the atmosphere each year. This is contributing to the long-term trend of rising global temperatures. The Orbiting Carbon Observatory 2, or OCO2, will be the first NASA satellite mission to provide a global view of carbon dioxide. OCO2 observations and atmospheric models like GEOS 5 will work closely together to better understand both human emissions and natural fluxes of carbon dioxide. This will help guide climate models toward more reliable predictions of future conditions across the globe.
Weird. It looks like the way they were visualizing it, that the northern hemisphere was being visualized differently than the southern. The same thing should be happening. That looked differently to me as well. The swirls are different. Yeah, exactly. So one of the things you can see is that, and we know this, is our air is constantly moving. That's helping to keep those really dense gases like carbon dioxide and argon from moving along so that they don't get trapped down in a basement or in a valley. And so we should be thankful that our Earth has different temperatures, the hot and the cold, and all the mixing that takes place. And the night and the day, that just keeps everything moving around. And so these gases won't accumulate. And so it's not a worry that we have. Now, one of the next things and last things about carbon dioxide that we need to talk about, actually we got two things. Greenhouse effect, of course, we just were talking about, is that it takes the visible light and traps the visible light as it gets converted into infrared light, and those molecules block the infrared light and create a warming effect. The greenhouse effect is very important. We actually need it. Without any greenhouse gases in our atmosphere, we would be about minus 20 degrees on average. On average, we're around 18 to 20 degrees on average throughout the year, in Celsius. And so a lot of people say, well, Earth is the right distance away from the sun. And that's true with the right gases that we have in our atmosphere. It's not just distance, it's distance plus the chemical makeup of our atmosphere. Because the distance without the right chemicals in the atmosphere, it's freezing cold. It would be ice most of the time. We would have an ice ball of a planet. So we need the greenhouse effect. It's not that it's a bad thing, it's just kind of it feels like it's getting more than it should be. So carbon dioxide, as they mentioned, is one of the leading contributions by humans, is what they said, okay, that we're having an influence on. So 99% of Earth's gases are not greenhouse gases. Nitrogen, not a greenhouse gas. Oxygen, not a greenhouse gas. Argon, not a greenhouse gas. Molecules that have 3 atoms or more, carbon dioxide, that's got 3, 1 carbon, 2 oxygens, methane, water, and a bunch of other molecules can act as greenhouse gases. So you need to have this 3 atoms or more in it. Is our blanket becoming too thick? Well, we need to think about everything that's going on there. Or is our planet overheating? When scientists have actually studied what is the main contribution of global warming, there is a different molecule that rises to the top as the main contribution to global warming. Can you tell from this table here what that molecule is? What molecule is the biggest contributor to global greenhouse warming? Yeah, it's actually water. That's why in that video they had to say that carbon dioxide is probably the biggest contributor to the greenhouse effect done by humans and our contribution there, although there's a lot of greenhouse gas from carbon dioxide that's happened naturally. Estimates have methane, actually could be overlapping with carbon dioxide. The problem's really complicated, and it may not just be carbon dioxide. Water vapor, I mean, it's all of these gases together that make the blanket. So I actually call it a quilted blanket because it's quilted with all these different gases in there. It's not just one thing. It's a much more complicated issue, but obviously if you can take care of one of those, perhaps the whole effect will go down. But it's a very tricky thing. We should look and we should not give up and say, well, it's too complicated, we can't figure it out. No, let's study it some more. Let's see how interconnected everything is and how it's been designed to work. But the biggest contributor to global warming is actually water, and we have very little control over that. One of the last attributes of carbon dioxide is its effect on pH. And I wanted to show you why we need carbon dioxide and its influence on water. Now, we said carbon dioxide plus water makes carbonic acid. You guys are good. You're still awake. All right. Man, I can go the rest of the time on carbon dioxide, but I got to get some nitrogen in there. I'm going to need some help from my lovely assistant. You're the handsome assistant, so I'm going to use the lovely assistant. Christiana, if you would come up here. All right, Carter's done this one a few times, and I appreciate your help that you've been up here. So what we're going to do is I'm going to use, I've got vinegar in here already. So I've got vinegar in this. And in here, on this side, I have some distilled water. And so distilled water, this effect works a little better. So I'm going to put some distilled water in here. Okay, we'll put some distilled water. And I'm going to put an acid-base indicator called phenolphthalein. I'm going to put a couple of drops in here. 1, 2, 3. Okay, well, I'll keep it on the table, guys, sorry. And now I'm going to put in something in here that's going to change the pH. And that substance that I'm going to use is sodium hydroxide. 0.1 molar if anyone's playing at home. Here, I'm going to put 3 drops in and stir it around. And that color change indicates that there has been a wide pH change, and we have now increased the pH. It's actually over a pH 9, almost to 10, and we get a nice pink color. You guys see that? Okay, that's water, distilled water on its own. Let's see the influence of carbon dioxide on the pH effect here. So I put distilled water in here already. You have to trust me that I did that. Christiana is going to help deliver some baking soda into this vinegar here. And as soon as she does that, yep, doesn't matter, just go ahead and put one in. I'm going to trap it. Yeah, hopefully this one is better than the one this morning. Yep, you're doing great. So this is just a Kleenex with baking soda in it, and she's going to drop it right in there, just push it right in there. And sometimes I make them a little too, the Kleenex is supposed to slow it down so I can get the lid on there. Okay, ready? And plop it in, push it in, boom, good. Okay, that gives me a second so I can put the lid on here nice and tight. Okay? You guys see what's happening? Okay? Baking soda and vinegar making carbon dioxide. I'm just pressurizing, I'm just making my own CO2 thing. You can do this at home. Go to the hardware store, get some tubing, drill some holes in there. Okay? Lots of pressure in here now. And I'm carbonating my own water. So it's a lot of fun here. And we're going to let it go and just give it a second. And then we're going to test this water right here for its pH effect and see if we can, well, let's see what happens. Okay? So you keep mixing it in there. And man, these things are really tight because there's so much pressure inside of them. So we have to be careful. Nope. It's staying room temperature. You would think almost this side, the acid-base reaction can sometimes be exothermic and produce some heat. All right. Now, you actually have to be careful on which side you open. I have a note that you can't see that says open this side first. I've opened that side many times first, and it actually sucks it just ruins it. All right. So we'll let the pressure off a little bit. Okay, and we're going to return the pressure back. And well, I'll just go ahead and pour this in here. And we're going to try to put about the same amount in there. And I can't forget to put in some of my indicator. All right. Christian, I would have you do this, but I think this bottle's been dropping some base, and I don't want to get on your hands. Okay, I'm going to put a few drops in there, and you can see it's starting to turn pink, but as soon as I swirl it, the pink goes away. Now, in about 3 or 4 drops, it turned pink before, and so I'm going to put some more in there. I see a little pink swirling around, but if I shake it, it goes away. What's happening there is it's neutralizing the base so that it cannot have a huge pH effect on there. The carbon dioxide is now acting as a buffer. And so I get some pink in there, but it goes away. So the carbon dioxide creates a buffer effect on water. That carbonic acid starts to create the carbonate buffer system, which is what our blood uses and the oceans use to maintain pH balance. So we do need the carbon dioxide, and we do need its effect. I'm putting just a lot of it, sodium hydroxide in there, and I just can't get it to change. There we go. Nope. Maybe that will go. Like I need a stronger base, and it just keeps going back. Powerful effect that carbon dioxide has on the pH change.
So you're saying that the carbon dioxide helps balance the pH in our blood?
It does. It acts as a buffer so that so when we're breathing it, it creates a buffer system in our blood to help maintain the pH balance. In our kidneys, it uses another buffer system called the phosphate buffer system. See, it's still not changing the color. So that's very important. That's a process that happens naturally, and it's part of the water and carbon dioxide reacting to form carbonic acid. Thank you, young lady. You may be seated.
So does the carbon dioxide create a higher level of alkalinity and a higher level of acidity?
That's a great question. So the question is, does the amount of carbon dioxide create more alkalinity or acidity? And it's more acidity. But it's a buffering effect. It can only go down so low. It can't go down to these really low acidic levels like a pH 1, 2, or 3. It's going to level off. But it will acidify. This is what everyone's worried about, the acidification of the oceans. It is lowering the pH a little bit. So that's also a very complicated process there. All right. But it's clearly making a buffer that's resisting the change for an alkaline material, sodium hydroxide. Great questions. Thank you. Carbonic acid, then, is part of the carbonate buffer system. Our bodies and the oceans use it for pH balance. And that's naturally happening. So we did our demo. All right. Another thing about carbon dioxide, man, I forgot, there's a lot of things. Carbon dioxide is food for plants. Many of us know this. We're taught this growing up. So I just wanted to reiterate this real quick. And so carbon dioxide is taken in by plants. And you take carbon dioxide plus water gives you what? Carbonic acid. But yet, plants take carbon dioxide and water and light for photosynthesis, and they make sugar and oxygen. That is not natural. And you say, well, yeah, that's natural. It's photosynthesis. No. The natural chemical behavior of carbon dioxide and water is carbonic acid, the carbonate buffer system. It is not natural to take carbon dioxide and water and make sugar and oxygen. Okay? You need a whole system to do that, and I'm going to show you the system. Okay? We call it photosynthesis. So respiration is the opposite. You're able to take those sugars plus oxygen and create carbon dioxide and water and energy. Okay? It's the reverse of photosynthesis. But that's also a very complicated process. Now, fires do it in a very simple way. They'll take carbon dioxide, they'll take sugars and oxygen. You can burn sugar and create carbon dioxide and hydrogen and heat and light. But to use it in plants, it's a very complicated system. And so I have, I think, one last video to help show that. Let's watch photosynthesis and how it can take carbon dioxide and water and make sugars and oxygen in an unnatural way.
Plants provide us with food to eat and oxygen to breathe. They perform this amazing feat by the process of photosynthesis. Let's take a closer look. Photosynthesis requires carbon dioxide, which diffuses into the leaf through small pores and then enters the cells. Inside the cell, carbon dioxide diffuses into the chloroplasts, where photosynthesis takes place. Chloroplasts use energy from light to transform carbon dioxide and water into sugar and oxygen. Zooming into a chloroplast, we see these flattened membranous sacs called thylakoids. Here, light energy is converted to chemical energy in the first phase of photosynthesis, the light reactions. The two green structures you see here are photosystems, large complexes of proteins and chlorophyll that capture light energy. An electron transport chain connects the two photosystems. Notice the small mobile electron carriers that shuttle electrons from one large complex to another. Now let's take a closer look at the steps of the light reactions. The photosystem on the left absorbs light energy, exciting electrons that enter the electron transport chain. Electrons are replaced with electrons stripped from water, creating oxygen as a byproduct. The energized electrons flow down the electron transport chain, releasing energy that is used to pump hydrogen ions, the blue balls, into the thylakoid. In the photosystem on the right, light energy excites electrons, and this time the electrons are captured by an electron carrier molecule, NADPH. The high concentration of hydrogen ions inside the thylakoid powers ATP synthase, producing ATPs. The light reactions in the thylakoid have produced two energy products, ATP and NADPH, that will now power the production of sugar in the Calvin cycle. The Calvin cycle takes place outside the thylakoids in the stroma, the thick fluid of the chloroplast. At the beginning of the cycle, carbon dioxide molecules combine with molecules called RUBP. The resulting molecules go through a series of reactions powered by ATP and NADPH from the light reactions. Sugar molecules known as G3Ps are produced. Most of the G3Ps are rearranged back into RUBPs that will begin the Calvin cycle again. But the important product of photosynthesis is the remaining G3P sugar. Some G3Ps are used to build glucose, which can combine into starch or cellulose. Still other G3Ps form sucrose. And some of the sugar is broken down by cellular respiration using oxygen in the plant's own mitochondria, generating ATPs that can power other work of the plant. Excess oxygen diffuses out of the leaf through the pores, while more carbon dioxide enters. With three simple ingredients, carbon dioxide, water, and light, plants produce sugar and oxygen by photosynthesis, powering plant metabolism and ultimately providing your fuel as well.
And water into sugar and oxygen. Did you guys follow that? Okay, my wife's going to hand out the quiz sheets afterwards. So we know how it's done. It's complicated, but we scientists have a pretty good idea, and this is what's taught in biology, freshman biology class, and in upper classes as well, as we get more detail in there. And it's believed that photosynthesis had to be one of the first things that evolved on this planet, if you subscribe to that theory, because that's the only way that's known to create oxygen. Because oxygen's so reactive, it wants to combine with everything and go away. So how do you make it? Living organisms are the only way. And it's one of the more complicated systems that we know of, and we're still trying to figure it out. And in my graduate work, I helped build some of those molecules that are very similar, and they're not easy to build. They're very complicated. We know how to do it. It's not that it's so complicated, God needed to do that. It's so complicated because we know how it works now. And you need a designer to get in there and put the parts together, because naturally it wants to do something else. And unnaturally or supernaturally, if you put the pieces together, you can create these amazing systems that will create sugars, that will create energy, energetic molecules like that we can derive energy from, and create oxygen. But how does that very, very complicated system become one of the first things that need to be on this planet? That blows my mind. I can't, that alone right there is, I can't believe that. Now, if it evolved after billions of years, okay, I could say maybe that might be something that can evolve after billions of years. But to the evolutionary story, that has to be one of the first things that's evolved. And I can't believe that complicated system there, with all those parts that have to be in there at the exact same time. You think a cookie is complicated with 9 ingredients? How many different ingredients did that take? Way more complicated. All of that has to be together at the same time, or it will not exist or function properly. So photosynthesis is a very complicated process because we know how it works. So we have the right amount of carbon dioxide in air. It's very little. It's enough to warm our planet. And it's enough to push into the water, create carbonic acid. It's more than we would predict by Henry's law, but it's there. And it does the jobs that we need to buffer pH, to warm our planet, and it's there for food for plants. And as we look at how much carbon dioxide levels could go to, you can see in my little chart here, 1% is enough to get people drowsy, 2%, you can hardly function, and eventually at 8% carbon dioxide, we would all die. So it doesn't take very much carbon dioxide before it becomes very toxic. So when it comes to carbon dioxide, it's already kind of at its highest level that at least most scientists would agree that we can't tolerate too much more. It's too thick. And we have enough carbon dioxide to feed all of our plants and create all the things that we need for energy. We know if we had too much, it would displace oxygen out. And so we don't want too much more because it's so heavy. We have this amazing photosynthesis process that returns oxygen back to us. As we utilize it for energy, the carbon dioxide buffers the oceans, it buffers our blood, and we know too much would kill us from the toxicity there. So I'm going to end it there, and my favorite talk is actually coming up next about nitrogen, and I had an experiment with that, but it's going to take too much time to talk about today. I want to give it its full value. So tomorrow I'm actually going to finish this part up, and this is called the overlooked molecule. And so just to set the stage, when I ask a lot of scientists about, well, why do we have nitrogen in our atmosphere, I get some pretty unthought through answers. And I said, well, can you replace it with anything else? And oh yeah, for sure. There's just another gas. You could easily replace nitrogen. It's not an exciting molecule at all. It doesn't do anything. It's the opposite of oxygen. And so I think it gets overlooked. And I think I see God's finger of design, God's hand of design in nitrogen. So we'll start with that tomorrow morning. And I appreciate you guys being here. And I hope you're starting to see how each molecule is involved in so many different things. And so if you're tweaking the levels, you got to think about all of that. And honestly, we've just scratched the surface. I cut a lot of things out. And so when you're designing a planet, well, one needs to think about all of those things. We have a question real quick here.
Nitrogen has to contribute to the photosynthesis because that's what helps make plants flourish is nitrogen.
Well, so nitrogen is suggested contributes to photosynthesis, not in a direct way, but in a tangential way. The parts, nitrogen we're going to see contributes to that process through the roots. And yeah, we'll get to the root of that problem. Okay, that was a lame one. Yeah. Keep this guy around.
You know, the ones that are slumbering.
Yes.
Can we add a little bit of hydrogen peroxide to our glass of water to increase the oxygen levels in our brain?
Okay, so the question is, if you guys need to go, you can, but maybe we'll make this our last question, and then if there's other ones, I'd love to answer these questions. So you asked if we could put hydrogen peroxide in there to get more just a few drops. No, you cannot. That will not help. If you want more oxygen in your brain, I suggest you just breathe deeply. Yeah, go for a walk, get some exercise, improve your lung capacity. Thank you. Let's end with a prayer, if you don't mind. Father God, thank you so much for this amazing world, and the deeper I dive, the more I just see your handiwork in place. And it's not because it's so complicated we don't know it, it's so complicated that it needs an engineer, it needs a designer to put it all in place. Your hands are all over this. And so we want to give you the glory and the praise for the designs that we see around here. And we want to be a part of that group of people that acknowledges you on a weekly basis on who you are and your great design that you have. So bless this camp meeting and our time together. And we just thank you once again for creating us and this planet and everything in it. In Jesus' name I pray. Amen. God bless you guys. If you have more questions, please come on up. All right.